The purpose of this lecture is to introduce the methods used to monitor and manipulate brain structure and function, or gyri and so on. But the temporal resolution is down on the order of milliseconds. It's a very rapid reflection of brain state, much faster than fMRI or PET. Now, embedded in the MEG is a technique called optical imaging, or EROS, event-related optical signal. And so this is a method closely related to fMRI, but it can operate somewhat faster, but it's at that larger spatial scale. Another technique, labeled TMS, stands for transcranial magnetic stimulation. This is a method that I'll show you that is used to manipulate the brain. It can operate on a shorter time scale, indeed one pulse at a time, for example. But it's got poor spatial resolution. It's on the order of a chunk of brain.
And it's my company. So if I say we have to pivot, we pivot. Okay. I have to go.
All right, let's make sure then tell them and then call me.
Another technique labeled red, outlined in red, optical imaging. This is a method used in animal studies. It's not typically done in humans, but it uses the relationship between blood flow and oxygen level and nerve function to look at the distribution in space of the cerebral cortex of active and inactive neurons. Finally, lower, we see a box labeled multi-unit recording, and at the very bottom, at the 10 micron scale in space, extending from 1 millisecond up to 1 day, is single unit recording. This refers to the signal obtained from individual neuron or a collection of neurons from a probe placed inside the brain close to the cell body of one or a few neurons. So this is the highest spatial and temporal resolution available for functional studies of the brain. Typically, this is done in animal studies, but more and more often, especially in cases of treating Parkinson's disease or epilepsy, for example, it's possible to get single unit or multi-unit recording signals in humans as well. Let me first summarize the methods used to observe the structure of the brain. One of the first methods discovered is X-ray. So this shows an X-ray of a poor individual who tried to commit suicide by shooting himself in the head with a crossbow. And so you can see the structure of the skull, and you can see the location of the arrow in this poor gentleman's head. It's something like Phineas Gage that we saw in a previous lecture. And so this case was reported in a journal article in 2005. We find it interesting that the authors, or perhaps it was the editors, felt compelled to draw an arrow pointing at the arrow. X-ray shows us the structure of hard objects, like bone and arrows in people's heads. It doesn't show us much about the soft tissue. Now, an X-ray is a flat image. You can do it at different angles, and so if the patient lays with his head oriented vertically, we get an image on the left. If he lays on the side of his head, we can get an image like on the right. With the advancement of computer technology and other technology, it became possible to do more of a three-dimensional X-ray. And so this is referred to as computerized tomography. So imagine a set of X-rays taken at all angles around the head, and now you've got, from each two-dimensional image, the ability to make a three-dimensional representation of the object in the field of view. CT also has a bit more sensitivity, so it allows you to see the inner structure of the brain as well as the skull. So we can see in the image in the upper right a horizontal section of the brain. We don't know which is left and which is the right hemisphere because we're not told if we're using the radiology convention or just the natural left is left convention. We see the butterfly-shaped lateral ventricles in the image, and other areas where the sulci dip in. But there's not a lot more that one can see here, especially not with the trained eye. The major technique used today to look at the structure, the interior structure of the human brain, is known as magnetic resonance imaging. So the image shows a photograph of such a device. It's a very, very large magnet, very powerful magnet, into which the patient or